Hello there. In this video, we're just going to showcase a few different probability distributions. So up till this point, we've been almost exclusively using the exponential distribution, but that is just for the convenience of having some distribution to throw in while we focus on other features. But I think it's worth taking a minute here to take a look at some of the distributions that are available in Q. So as always, let's import the QPython package. And maybe I should take a quick step back of like, why would we want different probability distributions? It's because in terms of real world data and in terms of the real world business assumptions that you can make, that sometimes you have properties, constraints, even though it's statistical in nature. Some distributions will fit reality better than others, or some assumptions are more reasonable than others when you're doing counterfactual or case scenario type stuff. So we may want to be able to throw in different probability distributions. So let's take a little look at some of the things that are available. Let's, as always, create network, and let's have our arrival distributions. And let's say that we're actually doing a multi-class network here, a type of Kelly network. So we might have class 0, and for class 0, or let's actually throw some of this stuff on different lines here just to stay a little bit organized. So for class 0, let's have q.dists.deterministic. I think we've seen this one before, where what this means is that it's going to use exactly the same value as sampled from this distribution every time. I would tend to call this something more like a Dirac delta distribution, but I think deterministic is basically fine. I would prefer calling it constant or degenerate or something else like that, but deterministic is fine. The thing is, sometimes you can have things that are technically distributions, but they're like conditional Dirac deltas, and so it's not a constant value every time, but we're in the nitpicking territory at that point. So let's go q.dists. Another option is there are empirical distributions, although it does count to spell empirical correctly, where you just take a collection of observations that you have, so literally some data. And in this case, maybe we've got some repeated values of 0.01 and then a value of 0.02. And what this class will do is it'll create a kind of probability mass function, I believe, an empirical CDF anyway, and I can't remember how it actually samples from it, but suffice to say, you pass in some values and it will induct a distribution from that. Okay, and this is just going to be a 2-node system, so we're done here with class 0, but we still need class, we're going to do 2 classes, class 1. In class 1, let's say their first arrival distribution, q.dists, is also a deterministic, value 0.2. And then next up, maybe to look at another new one, is to take something called PMF, or probability mass function, that takes a sequence of values as a list. Maybe we've got 0.2 as one of the possible values and 0.4 as a possible value. And then it also needs to take in a corresponding set of probabilities that have to add up to 1. In this case, we'll have a 50-50 kind of flip between whether the amount of time for the next until the next arrival is 0.2 units of time or 0.4 units of time. Okay, great. That should be it for arrival probabilities. Let's take a look at service probabilities. So let's grab service distributions. We'll start another dictionary here, just because we're doing multiple classes. Class 0 again. So now we're going to define probability distributions for the inter-service times of how long does a service take. It will not necessarily be the inter-service times actually, because that depends on the incoming demand, but for how long a service takes is, I guess, what we should think about this as. So the first one up here is q.dists, and this is the one we've seen many times, exponential. And that takes a rate parameter of, in this case, 0.6. We'll take another look. Well, let's take a look at one we haven't seen before, which is the log normal distribution. So the idea with that, of like what is log normal, is suppose x follows a normal distribution with mu and sigma, then a transformation of taking the exponential function of y produces a log normal distribution. And that has a particular advantage of becoming a non-negative. So y sim log normal, and you can parameterize this one in a couple of different ways, but let's basically say that there's like a mu and sigma, mu and standard deviation. So for a lot of like interarrival times, they need to be non-negative, and also service times need to be non-negative. And one of the nice things about applying this exponential function to a normally distributed random variable is that it turns all of the negative values into positive values. So that's very nice. And for that matter, turns 0 also into a positive value. Okay, well, this function can be parameterized with a mean and standard deviation in Q. So we'll have mean and standard deviation of, let's say, 0.5. And that's probably good for class 0. For class 1, let's take a look at what they're suggesting in the docs for class 1. Okay, so this is a good old classic distribution. This is a continuous uniform probability distribution. There is also a discrete uniform distribution. I can't remember if that's supported explicitly, but you could readily make one using the PMF option. Okay. And actually, in an upcoming video, we'll look at making custom probability distributions so that you can simulate according to whatever distribution you think is appropriate to your problem. Okay, so uniform, that's just uniform probability density over whatever the lower and upper values, in this case between 0.1 and 0.7. And then for this last one, we'll pick another one that's kind of an unusual one. It's a very unnatural looking distribution for many contexts, but if you've got very sparse information about something like what's the lowest value, what's the most likely value, these are kind of questions that you could ask a stakeholder, and that they might have some chance of giving you some kind of answer. Like you could ask them, what's the lowest value you've ever seen? They might tell you something. You might take exactly their value, or you might say, we're going to put a little bit of an uncertainty factor in there of making the lower than what they said, and their upper a little bit higher than what they said, just to allow for a little bit more uncertainty. Or you may stick exactly to what they've suggested for those times. But the mode is also relevant for going, what's the most likely thing? So a triangle distribution is a probability density function that just looks like a triangle. It's usually not an equilateral triangle. It's usually some kind of skewed triangle. Anyway, it's one of the ones that is more convenient for the purposes of getting requirements. Because if you ask people about lots of probability distributions like gamma distributions, I mean, they may have very little idea what things like the curvature of the probabilities looks like, but they may have memories of like, what's kind of like the most likely thing, what's the smallest and largest case ever observed, and that type of thing. So that's our service distributions. And so we've looked at, in point of fact, I may not even, well, no, let's complete the example. I was going to say, oh, we don't need to complete the example because this is all of the probability stuff. Let's just quickly recap on the distributions we've seen here. So we've got the deterministic distribution, which is going to give the same value every single time. We have this empirical distribution where you give it a set of observations and Q will make some induction about what the probabilities will be from that. Deterministic again, just for mixing things up again. I wonder if we should find yet another distribution to throw in as an example, but for now we'll leave it. The probability mass function, or PMF, is just a way of saying, well, for a finite set of values, you can explicitly define a probability mass function. If you need a probability mass function that is defined over an unbounded support, like the non-negative integers or something like that, then what you can do is define a custom distribution, which we will do another time. The exponential distribution, which is very common because if all you can say is something about like a rate or an average rate or something to that effect, then the exponential distribution is the maximum entropy distribution with that property over the non-negative reals. It's the only distribution with a maximum differential entropy, or I shouldn't say it that way. Among the different distributions defined over the non-negative real numbers, it is the one that has fixed mean and maximum entropy. Okay, and log normal is just coming about through a transformation of a normal distribution by exponentiating it. Also produces non-negative values. In terms of its moment generating function, it doesn't always exist, which is kind of interesting. And it's a distribution that's kind of got a bit longer of a tail. Uniform distribution is just a uniform probability density between some lower and upper. So you should get, it's the maximum entropy distribution for some bounded support on the real number line. The triangular distribution is nice for getting requirements from people because you just need to get them to make a guess about the lowest and highest possible values and what the most likely value is. Sometimes human experience can tell you those things. Okay. So that's what we're gonna stop at for the probability distributions, but I might as well follow the example in the docs all the way through here. So we need to specify routing behavior in this network because it is not just a single node. We'll just do zeros. And actually, I'm gonna just copy those values. There we go. And I'm going to also just copy that to get our routing matrices. So in this case, what these routing matrices are telling us is that none of the any of the customers, we'll call them, that are leaving a node don't go to any of the other nodes. They just simply leave the system. And then for number of servers, we have to specify for each node, and we'll just say that there's 1 and 1. Okay, we've got all that stuff that we need. And just to get that satisfying, we defined and ran a simulation feeling. Let's set up our simulation. This is also a good check to make sure that we've specified that the model is a valid Q network model. And just because we recently covered exact arithmetic, we might as well throw in exact. And then let's run it. So anyway, yeah, like running the simulation can be a check, not so much that you've got the correctly specified model, but just to make sure that as far as Q is concerned, that you have given it a valid simulation object and that it will run. So let's run this example distributions, and it appears to have run. Okay, with that, that was just a quick little sprint through some of the probability distributions that are supported in the QPython package. I hope that's helpful to you, and I will see you in the next video. Have a great day.